This conference will now be recorded.
Hello, my name is Scott Overpeck. I'm the warning coordination meteorologist here at the National Weather Service in Albuquerque, New Mexico. And today we want to talk a little bit about the careers in meteorology, what it takes to be a meteorologist. And to help do that, I've asked a couple of our forecasters here at the forecast office, Alyssa and Blair, to help answer some of those questions and just kind of talk about how they got involved in meteorology, and also some questions about meteorology and how we do forecasts and different things like that. So, Alyssa, can you tell us how you gotten started in meteorology? Was there any specific event or anything that kind of pushed you over the edge to become a meteorologist?
Yeah, hi, my name is Alyssa. I'm a forecaster here at the Albuquerque National Weather Service office. My story is I was interested in meteorology from a very young age. Actually, when I was a kid, I used to be terrified of weather, so much so that if I was, there was ever the threat of a tornado, I would have a panic attack. Well, there's one day in my hometown in Tennessee, there was this really nice thunderstorm that rolled through my town. It was a tornado warning storm. I didn't know it was a tornado warning storm. My mother, well, it wasn't the smartest decision on her part, decided we were going to ignore the tornado warning. We weren't going to tell me because she just didn't want to put up with one of my panic attacks. So for the first time ever, I was able to watch this thunderstorm and not be scared of it because at least in my mind, there wasn't going to be a tornado. And from that moment on, I was hooked. It was incredible. It was beautiful. And I wanted to know everything about our atmosphere and about the weather. And that was the day that I decided to be a meteorologist.
So what about you, Blair? How did you decide to become a meteorologist? Was there anything in particular that pushed you into the field?
Kind of similar to Alyssa, I was also just completely terrified of storms growing up. It's actually one of the first memories I have is trying to get to my parents' room and seeing lightning and hearing thunder and just being completely terrified. And then somewhere in elementary, my mother, who was the assistant news director at a local TV station, she had her broadcast meteorologist come to our school and show a bunch of videos. And it was really the first time that I had ever seen a tornado on screen, happening in real time. And it just, something about it just clicked. And I switched from being horrified and went into just being impressed and just wanting to learn everything I could about it. And from that point on, I would go chasing with my dad and I would make all sorts of questionable decisions. But yeah, and that kind of just started my whole journey. So very, very similar.
Well, great. So you have this interest in meteorology, and now it comes to deciding, well, how do I go about getting an education, learning about meteorology? So Blair, where did you end up going to college, and why did you decide to go there for meteorology?
So I went to the University of Alabama in Huntsville. I actually started my degree at Middle Tennessee State University, but Middle Tennessee State does not have any sort of earth system science or atmospheric science program. So I transferred about halfway through, which meant I got all my core done, at some place that was convenient for me and maybe a little cheaper. And then I moved about 2 hours south to Huntsville, Alabama. And a lot of that had to do with location. A lot of it had to do with being able to transfer in-state tuition. But they also, at that point, this was back in like 2013, they still had a very, very small program. And so I knew I was going to be able to get a lot of individual attention. I knew I'd be able to get out on field campaigns. And we were also co-located with NASA, so I would have opportunities there as well. So that was a huge driver for me.
Now that's pretty cool. You don't get the opportunity to partner with another agency like NASA very often and have those kinds of opportunities. So that's something also that people need to really kind of think about, is that that it's not just meteorology and just being in the core field. It's branching out and working with other scientists. So Alyssa, tell us where you ended up going to school and why you decided to go to, I think it was University of Oklahoma, right?
Yes, I went to the University of Oklahoma, which does have a meteorology program in Norman, Oklahoma. They have a really cool meteorology program. It's located in their National Weather Center, which is a building on OU's campus there, which also houses the National Weather Service in Norman, Storm Prediction Center, National Severe Storms Laboratory, the Oklahoma Mesonet. So you're studying meteorology in a building that houses a lot of professionals in your field. So it was really cool. It's a great program. You're located in Oklahoma. So for me, who loves severe weather, it doesn't get better than that, right in the heart of Tornado Alley. And I was able to work with the National Weather Service in Norman and work alongside them. I did some volunteer work for them, which helped to jumpstart my career and help get me into Albuquerque here.
Thanks. Yeah, I actually have a little bit different story. I went to a school called Creighton University for my undergraduate degree, and then I actually went on to graduate school at Texas A&M University and get a master's degree. Different backgrounds, allows you to do different things. And I think that's kind of the important thing. Often we get questions about, should I get a master's degree or a PhD in meteorology to have a career? And I think Alyssa and Blair shown, that's not necessarily true. You can still have a career in meteorology with just a bachelor's of science degree. Blair, do you know, what does it take to be a meteorologist in the National Weather Service? How did you apply, and what things did you have to do to meet the requirements for being a meteorologist in the Weather Service?
So to be a meteorologist with the National Weather Service, there are very specific courses that you do have to complete, most of which are housed in whatever, atmospheric science, meteorology, or earth system science degree that you might end up taking or doing. Additionally, like Scott mentioned, having a master's or a PhD can be helpful. In my case, like you said, I have an undergrad degree. And so instead of pursuing a master's, I was able to work with NASA, and I gained 2 years of professional experience doing that while I was finishing my undergrad. So having, just kind of a different background, it may not be operational meteorology related, but it gave me a completely different sort of, set of skills that I was able to, add to my resume that might set me apart from somebody else that may be applying. So aside from that, making sure that you're able to kind of get in some sort of shadow experience, either with an office nearby or any opportunity to kind of get a taste of what operational meteorology really is in the day-to-day, because it's not the same as what you might see when you go to school, and it's not going to be the same as like a field campaign or a research perspective. And they're going to want to know that you've experienced that and that you're kind of ready to take on the different challenges that operational meteorology is going to provide.
Yeah, and there are a lot of different opportunities in meteorology. So, we get asked a lot, question often, are you on TV? So, Alyssa, are National Weather Service meteorologists on TV, or what's the difference between what we do and what, say, a TV broadcast meteorologist does?
Yeah, there are a number of job opportunities for you in the career of meteorology. TV meteorologists are probably the first type of meteorologist people think about when they think about a meteorologist, because that's what they're exposed to, right? If you're watching local news every morning or every evening, that's who you see. We're not on TV, but you are familiar with what we do. So we do maybe a little bit more of background work considered to the folks who are on TV, but you are familiar with what we do. If you've ever been in a severe thunderstorm warning, a tornado warning, you see other products such as a winter storm warning. Those do come directly from us. And a lot of our forecast information as well, you may be familiar with that if you visit our page at weather.gov. So while maybe a TV meteorologist is maybe what people think about first, there are a number of career opportunities as well. As some people in meteorology stay in university, they do research to help us always improve on what we're doing, or maybe they become teachers to teach the next generation of meteorologists, or they go into the private sector to work for some companies, maybe such as the Weather Channel or AccuWeather. So there's a whole host of branches when it comes to careers in meteorology.
Yes, I'll even add, I spent about 2.5 years working for a private company before getting into the National Weather Service. And I would do marine forecasts for the Gulf of Mexico for oil companies, even shipping interests trying to travel across the Atlantic or Pacific Oceans. So there's a lot of different things that you can do in meteorology. It's not just being on TV. It's not just being, even working for the Weather Service. So we're going to actually kind of shift gears a little bit. We're going to kind of continue it into what sometimes we call an Ask a Meteorologist session. This is kind of something that we've done with school groups and other groups, but it's more impromptu. The children like to ask questions, so we thought we would try and address some of those common questions that people would have. A lot of people ask, well, what's the worst weather you've experienced? So Alyssa, what's the worst weather you've experienced?
The worst weather I've ever experienced was the late May tornado outbreak of 2013 in Oklahoma. I was in Norman, Oklahoma at the time. I was doing some summer courses there, so I was in Norman. And on May 20th, 2013, a EF5 tornado struck the town of Moore, Oklahoma, which is just about 10 miles north of Norman. That was an incredible day, a very scary day to see that tornado so close to home. Fortunately, I was fine. My apartment complex was fine. We were outside of the path, but that was a terrifying day. Even in Norman, we didn't have any communication. Cell towers were down, so I couldn't contact anybody in my family to let them know I was okay. And then just 11 days after that, on May 31st, we had another very large tornado hit the town of El Reno, Oklahoma, which is just northwest of Oklahoma City. So those last couple of weeks of May 2013, that was, I think, the worst weather I've ever experienced.
Yeah, what about you, Blair? What was the worst that you experienced?
Gosh, I was pretty young actually at the time. I would say maybe 12 or 13. So I'm going to age myself here real fast. But it was the 1997 Central Texas tornado outbreak. And my dad and I were camping like at Blanco State Park or something, just kind of in that same area. And that was the same day that the then F5 Gerald, Texas tornado just completely leveled a subdivision. And, this is in 1997. So, we did not have smartphones. We did not have radar in our pockets. And we were very foolishly driving around, literally looking for tornadoes as the thing is completely destroying, a good section of a town. And I just remember the day after kind of going to Gerald, and we were standing up on a hill and we were able to look down and see what was basically just, the foundations of homes that were just gone. And that has stuck with me for my entire life of just being like, wow, what can I do to help make this better? In the future, how can I make it so that people are safe? And yeah, that was the time.
Yeah, there's always weather experiences that kind of stick with you as a meteorologist. For me, more recently, I was a forecaster in Houston, so I went through Hurricane Harvey. So all the flooding there was probably one of the worst events I've been through. Even Hurricane Ike in 2008 was pretty bad. So definitely had a couple hurricanes in my experience. Not quite the tornado experiences you guys had. Another question that we get is what are some of the tools, technology that we use to make a forecast? So, Blair, you had an interesting experience. We had this winter storm recently, last couple of days, and you got to launch a weather balloon. Can you tell us about that?
Oh man. Yeah, so one of the tools that we use, and I'm sure you've heard of it, Scott just said, the weather balloon. It's an awesome little contraption that we basically a computer that we tie 100 foot of string to and then blow up this giant 8 to 10 foot weather balloon, and we send it up to the tip top of the atmosphere, and the little thing sends us readings every second that it goes on its journey, and we get temperature, we get relative humidity, we can get the winds, we get the GPS coordinates of where it is at that time, and we get the heights and the pressure. So it's giving us basically a snapshot of, if we have the atmosphere here, just right here in this moment of time, we get exactly what's going on the vertical scale of things. And it's incredibly helpful. From those, we're able to tell, especially with like the winter storm that we just had, are we going to be experiencing freezing rain? Are we going to experience snow? Is it going to turn into ice pellets? We can see all of that from these measurements. And so they're incredibly important. They happen twice a day, which for us in Albuquerque means 4 a.m. coming up here with standard time, 4 a.m. and 5 a.m., which means we get here at 3 a.m. And yeah, but they're incredibly important, and it's a global coordinated effort. So while we're here doing it, people in El Paso are doing it, people in Atlanta are doing it, people over in Hong Kong are doing it. It's really awesome that we're able to sample the atmosphere all together around the globe twice a day. And it's one of the neatest tools I think we have.
Yeah, Alyssa, can you tell us a little bit about the computer system we use in the Weather Service to look at data and make forecasts?
Yeah, we have some highly skilled computers here in our office that we use. We can pull in some model data, some forecast model data that can give us an idea of what we're expecting over the next several days. The balloons that Blair just talked about, those observations that our balloons are capturing twice a day actually gets fed into our numerical models. These models, do give us a general idea of what we're expecting maybe over the course of the next 7 to 10 days. They're not perfect. No model is perfect. So we have to rely on our own meteorological knowledge, our own expertise to find out, is what I'm seeing on our computer screen, is what this model is showing me, does it make sense? If it doesn't make sense, why? And what do I think I can improve upon? So not only that, our computers also pull in satellite data, radar data, so we can see what's going on in our area across the United States, across the world, and see, get a snapshot of what's going on in current time as well. And we use that in our warning operations. So we can use our radars to see if we need to issue any sort of severe thunderstorm warnings, tornado warnings, whatever the case may be. And that's what we use.
Yeah, it is a really a fantastic system. And we really have to depend on the computer technology to do our job. So learning some computer programming skills and some of those kinds of things really do help out with the job as well. One of the questions we also get, we go through the forecast process. So what happens if we get the forecast wrong? I mean, right? We're not perfect. We're human. We make a forecast. So what happens? Alyssa, what's kind of the process that we go through what happens when we get a forecast wrong?
Yeah, unfortunately, it happens sometimes. So we don't like for it to happen, of course. Our forecasts get updated twice a day, at the very least, twice a day. Typically, we push our forecast out around 3 a.m. and 3 p.m. every day. We can do forecasts more frequently if we find out maybe the forecast we put out there isn't really panning out. So if, I'll take our most recent winter storm that we had this week as an example. We had, widespread snow. We had areas of freezing rain. We had even some areas of rain and snow mixed in. So It was a very complex winter storm that we had to monitor using the tools that we had, our satellite, our radar, using the tools that we had, seeing what was going on, and updating the forecast kind of as we went along, updating the winter storm warnings and the winter weather advisories as we saw fit. So if we see a forecast that's not panning out, we make an update using our computer systems, and we send it back out into the world. And then once it's all said and done, we try to figure out, where did we go wrong? What happened? Did an area see snow that we thought was going to see rain? Why was that? What can I do? What can I take away from that? So the next time that I see this, I can do better and hopefully get the forecast right that time.
Yeah, we really do work hard to try and understand where the forecast went wrong, what we could have done better. We're constantly evaluating. It's kind of one of those things where I think sometimes we're harder on ourselves than anybody else. We're our own worst critics in that aspect. Blair, what do you think is the hardest weather to forecast? Or what's the most challenging?
I find that to be very subjective. I think no matter what meteorologists you ask, they're all going to have a different question about, or a different answer to that question. For me, I would very easily put all of that on winter weather. I grew up in West Texas. I didn't get to see very much snow. In fact, I think I have seen more snow here since I moved here than I have in my entire lifetime that I spent in Texas. So, I didn't get exposed to it very much. I, never got to see the meteorologists on the TV explain it. And then, of course, I went to school in Alabama, so we saw snow like twice, And the one time we saw snow, I got to go with soundings and, do launches and see like how that all works. But it's just something that it's very, very, very complex. And then beyond the atmospheric portion of it, beyond that being complex, we have the added element of terrain here and the added element of what happens to winds when it interacts with that terrain. So we have upslope and downslope flow situations that are going to enhance some of these more winter type precipitations, events. So for me, it's always been just kind of in that area of like, is it sleet? Is it snow? What is it going to be? When is it going to get here? It's just such a different world than what I'm used to, which has always been convective, severe storm type stuff, which I almost feel like I could do in my sleep because I've lived for it.
Yeah, what do you think, Alyssa? What's challenging for you? What's the most forecast challenge that you've had?
I completely agree with Blair.
Yeah.
My background is in severe weather. I went to the University of Oklahoma because of the severe weather. So I feel much more comfortable forecasting severe weather, winter weather, for all the reasons that Blair said, the different types of wintry precipitation, the terrain, all of it makes it very challenging.
Yes, winter weather certainly complicates a lot of things. I'll even mention the aviation forecasts we do. These are called TAFs, or terminal aerodrome forecasts. And when winter weather happens at airports, it really makes a mess of things. And so the airports want to know, when will it start snowing? When will it stop snowing? When will it be the most intense? When would visibility drop down to below a mile or less? How high are the clouds are going to be, the ceilings? It's just, it can get kind of hairy. And then if there's a mix of snow with sleet, they want to know about that. They want to know about freezing rain, when that might happen. So yeah, the combination of trying to forecast for airports with winter weather is a big challenge. We're going to go into some kind of more basic questions, but can just kind of things that people are curious about. When you think about a raindrop, Alyssa, how big is a raindrop? What does that look like? And while you're kind of discussing that, I'm going to pull up a graphic and kind of help people understand what a raindrop looks like.
Sure. Well, it depends on the height that the raindrop is in the atmosphere. So you can see there, On the graphic, as we start, maybe, at the top in a thunderstorm, it's rounded, it's maybe around a quarter of an inch. It starts to fall, and as it starts to fall, it loses that rounded shape, and it flattens out. You can think of it maybe as like the shape of like a hamburger bun. So it flattens out and it continues to fall, and as it falls, the speed that it's falling causes it to kind of break apart. And then as it nears the surface, you might see a raindrop that is maybe more of what you're used to, that teardrop shape. And by the time it hits the surface, it's maybe around 1 to 2 millimeters in diameter.
Right. So it's not the typical, teardrop that we kind of think of as a raindrop. It varies in size, and raindrops even collide with one another and can form bigger raindrops and then fall apart and break up. And so there's a lot of things going on there. Our next question is how do rainbows form? So Blair, can you kind of go through some of these? How does the rainbow form?
So you're going to always see your rainbows when you got rain that's falling and the sun is passing through it, right? And you might also see them, say, if you're walking down the sidewalk and you have a sprinkler system on and you see light passing through that. So our two main things that we need are obviously light and then a water molecule. And what happens is the light starts to pass through that water droplet, it slows down, it reflects off the back and starts to scatter out as the many different colors, as you see, which are also all the same colors of the electromagnetic spectrum, the visible portion of it. And so that's part of the reason that we also have such beautiful, beautiful sunsets here. The whole thing is called scattering. That's the technical term for it. And when we have clouds up in the atmosphere and we have the sun setting here, especially when we have episodes of Virga, which is basically rain that's evaporating before it hits the ground, that causes sunlight to scatter and make all those beautiful colors. So they're actually the same process. It's really, really cool. But yeah.
Yes, it is. And you actually have to have some pretty big raindrops for that to happen as well. Okay, so one of the other common questions we get is, what's the difference between snow, sleet, and freezing rain? We've kind of talked on this a little bit with winter weather. So Alyssa, you think you can kind of go through the process of, what makes the different kinds of winter precipitation for us?
Yeah, absolutely. So the different types of winter precipitation, whether you're going to get snow, sleet, freezing rain, or just plain old rain, actually depends on the temperature profile of your atmosphere. So as you go up into the atmosphere, the temperatures as you go up are very, very important as to what type of precipitation you're going to get. If you want snow, then you need a temperature profile that is below freezing, which is below 32 degrees Fahrenheit, for your entire atmospheric profile. So your entire temperature line as you go from the surface up into the atmosphere is all below freezing. Where the sleet and freezing rain comes into play, that's because you have an area of warm air, an area that's above freezing, somewhere in your vertical profile. And the difference between sleet and freezing rain is dependent on how deep that warm air is and how close to the surface it is. So for sleet, we have an area of warm air. Perhaps it's not so deep or it's not so close to the surface. So as you have snow that falls down into that warm layer, it's going to melt. And then it comes out of that warm air, comes back into the part of your atmosphere that's below freezing, and it refreezes before it reaches the surface. So that's sleet. It's snow that's melted and then has refreezed before it hits the surface. Freezing rain you might get if that depth of that warm air is deeper or it's closer to the surface. So again, at the top of the atmosphere, at your cloud, you have snow that's falling. It goes through that warm air, it melts, and it comes out of that layer of warm air but it doesn't have time to refreeze. So when it hits the surface, which at your surface you have freezing temperatures. So it comes out of that warm air, it doesn't have time to refreeze, but your surface is freezing. So you have the liquid raindrops, it hits the surface and it freezes, and that's freezing rain. Rain, you may start as snow as it comes out of the cloud, but you have warm air that extends. You have a deep layer of warm air that extends all the way down to the surface. So the snow melts and turns into rain, and it's rain all the way down to the surface. So it really just depends on the temperature profile. If you have a layer of warm air, how deep is that layer of warm air and how close to the surface is it? And that plays a large part into what type of wintry precipitation you're going to get.
Yes, that's a great overview, and you know, it's very common to get all three in a winter storm, and that really makes travel conditions very hazardous as well, and just a lot of different impacts. We're going to actually shift gears a little bit, get out of the winter weather, and one of the more common questions is, how does a tornado form? So Blair, this is kind of a lot going on in this graphic with what we call a supercell thunderstorm that is rotating, but you just kind of got to briefly go through what it is, what it takes to get a tornado, and what kind of thunderstorm it takes to do that.
So how tornadoes precisely form is still under much study. We don't really know. We know a lot of the processes that are necessary for them, and for the most destructive tornadoes that we've had, they all share a thing in common, and that would be they come from a supercell. And a supercell is a rotating thunderstorm that has what's called a mesocyclone. And in this graphic, you can kind of see that you have the rain or the hail, you have the cumulonimbus cloud, you have that big overshooting top. It's a very classic looking cloud that you've probably seen. And then as you move further to the left, you see that kind of descending wall cloud. So that would be rotating. That's one thing to look for. There's a big difference between having a rotating wall cloud and having what we call scud, which is just low-hanging clouds that just look menacing, that aren't actually going to cause tornadoes. But then you have this rotating wall cloud, it descends, eventually you do start to see a funnel cloud, and that will reach the surface. You can ultimately get tornadoes with non-supercell storms. You can also get them in quasi-linear convective systems. And you can also they have some interesting ones that happen kind of more in Wyoming and Colorado, and even the northern parts of New Mexico, that are less driven by these mesocyclonic processes. They're usually very similar to landspouts. They're very, very weak, and almost look more like dust devils than anything. But to have any sort of destructive tornado or any sort of classic tornado that you're used to seeing, you need this situation with the supercell and the mesocyclone and all those rotating features.
Right. So generally, we have some what we call spin in the atmosphere, winds at different levels that allow this spin to develop, and basically get sucked up into the thunderstorm and stretched out. And that's kind of the general basic principles. There's still a lot of physics that go into what cause it, and there are times where we think a storm's going to produce a tornado, but it doesn't. And that's kind of the tricky part, is that there are some factors in the atmosphere that we just don't quite understand that go into why one storm will create a tornado and why another storm that looks like it has those same types of characteristics, but it doesn't. So there's still a lot of research to go on with tornadoes. Finally, with lightning, how does lightning form? Alyssa, do you want to kind of take us through how that process, how lightning forms with this kind of diagram?
Sure. Well, in a thunderstorm, you have all sorts of particles that are within your thunderstorm. Some of these particles have positive charge. Some have a negative charge. You can think of it as like a battery. One side of the battery, you have the plus sign for the positive charge. The other side of the battery, you have the minus sign for the negative charge. These particles, as they interact with each other, bounce off of each other, you get, some sort of a static electricity. that descends from base of the cloud and sometimes down to the surface, and that is lightning. But I know that Blair, her big thing is lightning, so I bet you she has a great explanation.
Oh gosh, I could talk about lightning all day. So yeah, just kind of jumping off of what Alyssa said, you know, as your thunderstorm is growing, you're going to get ice crystals, you're going to get, you know, super cold liquid water, and those things are going to come together, create grapple, and it's kind of like, you know, going into your laundry room, you know, unpacking fresh laundry. You know, as stuff gets friction, it starts to spark, and you have that static electricity, you run out and you touch your brother and shock him on the nose, that sort of thing. So that same thing is happening in the cloud. All this stuff is getting tossed around, and eventually you get charge separation. So we get this positive over here, we get this negative over here, and maybe perhaps there's positive at the ground that negative charge sees and goes, I want to go down there and check that out. And so you get what you see in the second image of a stepped leader that goes down to that positive charge and meets it, and then you get a return streamer that's taking that positive charge back up into the thunderstorm. And the whole goal here is to have balance. So if you have any sort, you can end up having, you know, these positive charges at the top of the cloud, you can have them discharge. And a lot of times with that is where we get the bolts from the blue. So those are the ones that, you know, you might not hear thunder, you might not even really know that there's a storm near you, and they can strike, you know, 7 to 10 miles outside of that storm. And so it's incredibly interesting how adaptable the storm can be and how these charges can reach out even beyond what you would expect the scope of them to be.
Yes, thank you, Blair. That was both of you spent some great time explaining that. And you know, before we leave, we do want to make sure that people are aware that, you know, we want you to be safe in weather as well. So when it comes to lightning, we have these sayings, you know, when thunder roars, go indoors. For flash flooding, turn around, don't drown. You get tornado warnings or severe thunderstorm warnings. Best places to go inside and seek shelter. So that's kind of why we do this, is that we want to keep people safe. Yes, we are passionate. We love weather. We enjoy it. It's exciting. We've worked hard to make the best forecast possible. We've got great tools to do it. But we want to share with everyone that you know, this is a fun field. It is incredibly challenging, but we enjoy it. And I think that's kind of one of the things that we all share here in the office at the Weather Service in Albuquerque, is that, you know, we really enjoy what we do and want to share it and want people to be safe as well. So thank you for joining us for this session of Ask a Meteorologist. And if you have any more questions, please feel free to contact us at the National Weather Service in Albuquerque. Thank you.